Hey everyone, welcome back to TechLab. Today we are unpacking one of the most talked about drones in the world, the Shahed 136, and I will show you the technical secrets that make it so unique. Imagine a flying robot that costs a fraction of a missile. You can travel over 1,000 kilometers and strike with precision. Not a quadcopter, not a toy, a purpose-built endurance drone. This is the Shahed 136, but today we are not talking about politics. We are treating it as an engineering case study, a chance to learn real design lessons for drone and robotic projects. Let's start with the airframe. The Shahed 136 uses a cropped delta wing with a small wingtip fins. Why this design? Because delta wings are simple, stable, and efficient at subsonic cruise speeds. They provide a large internal volume for fuel and a good lift-to-drag ratio for long flights. But there is a trade-off. It's not maneuverable. This drone isn't designed for dogfights or aerobatics. It's built for endurance, flying in a straight line for hours, not pulling sharp turns. For comparison, think of a paper airplane vs a racing drone. One glides far, the other zips around corners. Choose your airframe shape based on mission profile. If you need long-range mapping or agriculture, delta or flying wing designs are excellent. But if you want agility and precision hover, go with multi-rotors or hybrids. Mission defines design. The Shahed 136 is powered by a small piston engine, specifically the Mado MD550, a 4-cylinder 2-stroke engine producing around 50 horsepower. It's noisy. So noisy it's nicknamed the moped drone. But here is the key. Energy density. Gasoline has around 12,000 watt-hours per kilogram, while today's lithium-ion batteries average about 250 watt-hours per kilogram. That's a 50 times advantage in energy density. That's why piston engines still dominate endurance drones. Electric drones are clean and quiet, but they can't yet match the range of gas-powered platforms. Of course, piston engines bring disadvantages: noise, vibration, higher maintenance, and a big thermal signature. Pick your propulsion system based on endurance and mission needs. Electric is great for short, quiet operations. Piston or hybrid systems win when you need hours of flight. Now the brain of the system, Avionics. The Shahed 136 combines GNSS navigation, GPS, and GLONASS with inertial sensors like accelerometers and gyroscopes, fused in an extended Kalman filter. This lets it fly pre-programmed routes without a live pilot. But here is the weakness. GNSS signals can be jammed or spoofed. That's been reported many times in modern conflicts. When that happens, the inertial system helps, but it drifts over time. Later variants, especially those locally produced in Russia, reportedly include anti-jamming antennas known as CRPAs to improve resilience. Never rely on a single sensor. Autonomy should be sensor redundant. GNSS plus IMU plus vision or train-based navigation where possible. That's true for delivery drones, inspection robots, or even Mars rovers. Now let's talk about one of the most striking features of the Shahed 136. Unlike high-end missiles or aircraft that are launched one at a time, this drone is designed to be fielded in large numbers. Why? Because individually each drone is modest in speed, payload, and sophistication, but in a swarm they become something far more powerful. The deployment system is deliberately simple. A rack of drones mounted on a track, each boosted into the air with a small rocket motor, allows dozens to be launched in minutes. This creates what engineers call a saturation effect. Defenders are forced to track and intercept multiple small, low-flying targets at once. Every interceptor missile they fire costs many times more than the drone it destroys. That's the cost exchange problem. Cheap attackers versus expensive defenders. In swarm logic, the strength isn't in the single unit. It's in the system of many working together. Some act as decoys, others carry warheads, and together they overwhelm defenses through sheer numbers. And here is the design lesson. When you think in systems, not just in single machines, you unlock a different kind of power. Whether it's delivery drones, agricultural fleets, or inspection robots, coordination and numbers can matter more than raw performance. Here is where engineering meets economics. Open source estimates place each Shahed 136 at roughly $20,000 to $50,000, while the missiles used to intercept them can cost several times more. That's called a cost exchange problem, and it's as much a system design issue as an engineering one. The Airframe and electronics use commercial off-the-shelf components, microcontrollers, RF chips, power boards, that keeps costs down and simplify logistics. Launch is via simple truck racks with rocket boosters, no expensive airfields or runways needed. It's not just the drone itself. True system design includes production choices, logistics, and deployment methods. In civilian robotics, think about how your robot will be transported, maintained, and scaled, not just the core design. And that brings us to the end of today's breakdown. We have seen how aerodynamic efficiency, swarm-capable deployment, and adaptable electronics turn one small airframe into a big engineering story. From now on here at TechLab, we will be doing more videos just like this, taking real-world projects as case studies and pulling out the lessons that we as engineers can actually use. Every machine has a story and every story has engineering principles we can learn from. So make sure you subscribe because in the next episode we will keep diving into these fascinating designs and together we will turn technology headlines into hands-on knowledge.